All right. We're going to look at Faraday's law today. And in order to do that, we're first going to look at some conceptual ways to generate an EMF, and then we'll look at specific example problems of the general case of Faraday's law and then a motional EMF problem. So to begin, we're saying that we have a loop that's in a B field that's perpendicular to the loop's plane, and we want to figure out 3 unique changes that could induce an EMF in the loop, drawing sketches in each case. So first, we need to know how we actually induce EMFs. And as stated in Faraday's law, the induced EMF is equal to the change in flux through the loop. So anytime you have a magnetic flux change in your loop, you will get an EMF induced. And I dropped the minus sign because we'll typically just talk about magnitude and get the direction correct using Lenz's law. So we need to figure out how to change magnetic flux. So magnetic flux is most generally written as B times A times cosine theta. So, because again, flux can be thought of as the amount of field penetrating an area. So it depends on the magnetic field strength, because more field, you get more penetration. If the area is increased, you get more penetration. And then also we have this cosine theta, where if the field is angled, only a component will actually be piercing the loop. So our 3 changes are going to be changing B, A, and cosine theta. So the first way, this is probably the easiest way to think about, is just changing the value of B over time. So again, first, we'll just think about sort of this case where we have our loop, and then over time, we're going to have some initial B field, and then we're just going to make it larger. So we can make it larger in magnitude or smaller. Either way, we will get induced EMF. Because with more B field, we're getting more flux. So as long as we increase that over time, we get an EMF. So there's my first one. Change the value B over time. Increasing B changes a change in flux, and thus induces a current. This one would be clockwise. All right, so there we go. We can change B. We can also change area, A. This one might not be as an achievable, depending on what kind of conditions you have. But one thing we could do is we could, assuming the loop was malleable in some way, we could somehow stretch out the loop and change the area. So we could say we had a small loop and then we had a big loop. So if we somehow changed this area and just kept the field constant, well, then it would change the flux because you have the same field through a bigger area. So if you expand the loop or contract it, it'll cause a change in flux and induce a current. Once again, this one would be clockwise again to oppose that change in positive flux. And then last, this one is also very common. It's rotate the loop. It's very important that we can't just rotate it along any axis. It has to be rotated along axis such that there will be a change in the angle that the B field makes with the loop. So if I think of my loop sort of right here, and my B field pointing out like that, well, if I rotate sort of around where that B field is pointing, it's definitely not going to induce an EMF. But maybe if I rotate it around sort of this axis right here, we'll see that it does generate an EMF, because there will be points where the field is entirely parallel now to the loop. So it actually wouldn't cause any flux in that case. So since we're changing flux, we are inducing a current. All right, now for an actual free response. So first we will do one with Faraday's law, and then we'll do a application with EMF. So a squared loop of resistance R and length L is placed in a region of magnetic field that's into the plane of the loop. The magnetic field is gradually increased in magnitude from 0 and varies according to B equals A times T cubed, where A is constant. So the field is gradually increased during the time interval T equals 0 to T equals capital T, after which it's held constant. So what we have here is basically this situation where we have a square loop, and we are just slowly sort of increasing the magnetic field in the negative direction. So first, for the direction of the induced current in the loop, well, we are increasing the flux in the negative direction, so that is a negative flux change. So we have to use our right hand and curl our fingers around that loop in such a way that our thumb points up to counter that change, and that would be a counterclockwise current. Because again, if we think about our loop, if we draw it counterclockwise, we see that if I curl my right hand around that way, I do in fact get a magnetic field that points out of the screen, and that would oppose the flux change. So that's how we apply Lenz's law. So we can see the explanation here. Since the magnetic field is increasing into the page, flux change is negative, so we need a positive magnetic flux contribution from the induced current. All right, so now we'll get on to the actual derivation. So first, we're going to find the induced EMF in the loop as a function of time. Pretty classic question. So if we're finding the induced EMF, we are simply just finding the rate at which the magnetic flux is changing. And it's important to note that the flux change is not just the rate of change of the magnetic field, it's the rate of change of the magnetic field multiplied by the area. And typically only one of these will change at once. So in our case, the area is constant, so it's just going to be the rate of change of the magnetic field multiplied by the area. So now looking back at our specifications here, we see that the loop is just a square of length L. So that makes our area pretty easy to compute. And then dB dt, well, we're taking the derivative of AT cubed. And then we have to multiply by that area of a square of L squared. And we'll get 3AL squared times T squared. And I just put the T squared at the end so we can know our functional dependence here. And then current, very easy if you already have EMF, because we can just use Ohm's law. So if delta V is IR, then that means that the induced current is just going to be the EMF divided by resistance. So we're just taking our previous expression and dividing by the resistance of the loop. Pretty straightforward. Now we start to just keep adding on things here. So now we're going to go for the power dissipated. So we have three choices for finding the power dissipated. We could use the definition, I delta V, or we could use Ohm's law and make two substitutions in here. So we could do one in terms of current only, and one in terms of potential difference only. Generally, I would pick the delta V squared over R for these Faraday questions, just because the EMF is probably the thing you know first. And I'll fix that. So we're just going to use the EMF and divide by resistance. So that the EMF induced, we said, was 3AL squared T squared, and the resistance is R, and we square that EMF. And then making sure we hit every term with the square on top, we get 9A squared L to the fourth over R, and then times T to the fourth. And again, I put my functional dependence on T in the end, just so I know what I'm looking at. All right. So now total energy dissipated. And the fact that it's between two times gives us an indication that there's an integral involved. And we know that because power is the rate at which energy is dissipated. So to find all of the energy dissipated, we can just add up all of the contributions from each tiny time. So if we add up all of the instantaneous rate of energy dissipations, we get the total energy. So the energy is just going to be integrating from 0 to capital T of our power, which is 9A squared L to the fourth over R times T to the fourth dt. And this looks like a mess, but really 9A, L, R, all those are constants, so those don't matter. So we're just going to get 9A squared L to the fourth over R times the integral from 0 to T of T to the fourth dt. And this antiderivative is just T to the fifth over 5. Basic power rule. Nothing weird happening with the lower limit, so this just becomes 9A squared L to the fourth, and then we get our capital T to the 5 over 5 also tacked onto this. All right, now for sketching some graphs of each of these quantities, labeling the extreme values. So first, the magnetic flux through the loop, assuming magnetic field out of the page generates positive flux. So again, what we have going on here is we have a square loop, which I guess is in fact a rectangle. Don't know why I wrote rectangle, but regardless. We see that we have this sort of magnetic flux that's increasing into the loop, and we said define that as negative. So what we should have is some sort of negative increasing flux. And we do know that B was equal to AT cubed. So this means that the maximum value of our magnetic flux is going to be A times big T cubed, and we'll put a negative in front of that because we know it's going to be into the plane. And due to this dependence, so this is the maximum value of B, and then to get the maximum flux, well, we know it's just going to be B times A. So we have to make sure to multiply that T cubed by the square of the length to get the area. And then we know that it's held constant after that. So we're just going to have some sort of a increasing magnetic field in the negative direction. And then the magnetic flux is held constant. So we want to label that extreme value here. So down here is where that max value occurs, even though it's a minimum, it's maximum magnitude. The flux would be negative AT cubed L squared, which is just BA. We just found the maximum value of BA. All right, now we'll find the induced current. So it's important to note that current is going to be the induced EMF divided by R. And the induced EMF is equal to the rate of flux change. And we actually already found that. On the previous part, we did find that the current, in magnitude at least, was just equal to 3AL squared T squared divided by R. So since this is increasing with time, we know that it's going to reach some sort of a maximum value somewhere. So it is important to note that since the magnetic flux is held constant, the field slash flux is held constant after this T equals capital T, there will be no induced current after this because we have a constant magnetic field. So therefore, we know that we'll have no induced current from capital T onwards because the flux is constant. But we do know that we are going to have an increasing current quadratically with maximum value occurring at T equals capital T. And now we just have to decide if it's positive or negative. Well, we said in the previous part, if we're increasing our negative flux, then we need a counterclockwise current circulating in order to counter that. So I'm just going to draw a positive increasing current right here. And I'm going to make the maximum value of that this 3AL squared T squared over R. All right. Now we just need to indicate whether these two graphs are consistent with one another. So remember that according to Faraday's law, the induced EMF, and therefore the current, should be proportional to the rate of magnetic flux change. So if I look at this graph of flux, the current graph should be the negative derivative of that. So let's see. We have a negative cubic and then a constant. So then we should get a positive quadratic and then 0. And that is, in fact, what we get. So going in the actual wordy explanation here, the two graphs are consistent because the induced current is proportional to EMF, which depends on the rate of change. So as such, the current graph should look like the derivative of the magnetic flux graph. And the sign is reversed just to show that Lenz's law is being followed. In the same scenario, except we direct the field out of the page. So how would that affect the graphs? So again, just the same problem, except instead of the field increasing into the page, the field will increase out of the page. So we could probably guess that since this changes the magnetic flux through the loop, it's going to change both graphs. And really, this is just a simple sign change. Because if you change the sign of the flux, you change the sign of the current. So both graphs would change in sign, meaning you reflect them across the x-axis. Because if you change the magnetic field sign, you change the flux sign, you change its rate of change, and therefore the current direction. Because if you increase out of the page, you need this sort of clockwise current to generate a magnetic field in the other direction now. So it's just a simple reflection. All right, now onto motional EMF. This is a pretty classic setup where we have some sort of a square or rectangle loop of wire that's being dragged into a magnetic field. So it's rectangular, it has some resistance and mass, and it's important that it's moving at a constant velocity v1. So we begin with the right side at x equals 0 into a uniform magnetic field pointing into the plane of the loop. Spelling error here, or sorry, just error here in my question. The region of magnetic field spans from L to 3L, so this means that the loop can fully fit in the field. So it's going to enter, it's going to get more and more flux, then it's going to stay in the field for a little bit longer and then exit. And it's important that there's some external force that helps it go in and out to maintain this constant speed. So now we're going to look at the direction of current flow within the rectangle when the right side of the loop is at each of the following positions. So I guess from this diagram, it's first important to figure out what is going on, meaning when the loop is partially in the field and partially out and fully in, because that's going to help us figure out our induced current if there is any. So when x is 1.5 L, this means that the right side of the loop is at 1.5 L. So this corresponds to our loop being exactly halfway in and halfway out of the magnetic field. Because it starts to enter at x equals 1 L, and it would be fully in at x equals 2 L. So this means that there's all this magnetic field over here, and the loop is currently entering. So as such, there's currently an increase in negative flux in the loop. So we have a negative flux change. And as a result, we need a counterclockwise current in order to generate a positive magnetic flux to oppose that. Because again, the loop does not want all this negative flux increasing through the loop, so it generates a positive flux. So this is counterclockwise, and I just abbreviated it. X equals 2.5 L. So the loop is fully in at 2, and then it starts to exit at 3. So this represents when the loop is fully in the magnetic field, and it has not exited yet. So there's still magnetic field on both sides of the loop at this point. And even though there is flux through the loop, there's no change in flux, so the loop is happy. so to speak, at this point. There's no flux change, so this would be zero current. This is a key thing with these motional EMF problems, that once you're fully in the field, it stops experiencing that magnetic force, well, a net magnetic force at least. So we actually don't need an external force to help pull the loop at this point. It's only in and out when we get those flux changes. And as such, here's sort of the inverse of case one, where now we're exactly halfway out of the B field. So the loop is exiting here. So there's still field on this side, but there's no field on the right. So as such, it is losing negative flux, which would be a positive flux change. And as a result, we would get a clockwise current to try and generate negative flux to restore it back to its original state. Because it was happy having all of this negative flux in the loop when it was fully in, as in case two, but now it has to restore that, or at least attempt to. So notice that these two current directions are inverse. When you pull in versus pull out of the field. All right, now a big graph for us. Magnetic flux through the loop, assuming out of the page generates positive flux. Okay. So once again, I like to do these big physics graphs by knowing sort of our extreme case. So first, I know that the loop is going to start with zero magnetic flux inside, because it has not reached the magnetic field yet. And it only starts to reach the magnetic field at x equals 1L. And then also I know it has fully exited the field after the right side has reached 4L. So I know that there will be some segments of just zero magnetic flux through the loop, sort of at the ends here. And then I also know that the loop is fully immersed in the magnetic field at 2L, and it continues until 3L. And at that point, there's no flux change in the loop, so it has some sort of maximum value. And now we just have to figure out the connector. So it will be a linear connection for each of these, because it is a square loop, so the same amount of area is being added into the field throughout this process, because you have a constant speed. Now we just have to figure out what this maximum flux value is. Well, we were given that our rectangle was L by 2L, and we had a magnetic field B into the plane of the loop. So that just makes this value negative 2BL squared. Because the area of the rectangle is 2L squared, and there's a field B perpendicular to the entire loop. So now we're looking at the induced current within the loop, denoting a counterclockwise current as positive. So we can just look at the negative slope of this graph in order to tell us what the answer will be, because once again, we do know that this is equal to negative of the induced EMF divided by R, which again, the EMF is the flux change. So first of all, notice that there's only induced current in these two small regions, 1 to 2L and 3 to 4L. So everywhere else it's zero, because you're not changing the flux before you enter the field. You're not changing the flux when you're fully in the field, and you're not changing the flux when you're fully out of the field. Then we got to figure out what's going on for the other two. Well, notice that just looking at the graph, we have two linear functions. So we are going to have constant current when we're entering and exiting the field. So first, we're getting negative flux when we enter. So we need to have some sort of a constant finite value of current induced as we enter, because it's going counterclockwise. And then similarly, as it exits, we want to have the same amount of current, trying to estimate here, that's going clockwise. And don't really worry about the circles if it's open, closed. I'm doing a rough sketch here. And then we also know that for motional EMF, the induced EMF is given by VBL, where L is the direction of, where L is the length of the loop in sort of the direction of the velocity. So VBL is our maximum sort of EMF. So we know that this value will be VBL over R, and this value will be negative VBL over R. And I guess it did give us in the problem that the speed of the loop was V1, so I will write V1 here. And again, notice this is consistent with what we found up here, where we said there would be a counterclockwise current in this region and a clockwise current in this region. Now we'll look at the force required to keep the loop moving at constant speed. So first, when the loop is entering the magnetic field. So the reason we need this sort of external force in the first place is because if we're entering this region of magnetic field, the loop is going to get pushed out. So there's this magnetic force that gets applied to the loop just by being in the magnetic field. And it always goes to oppose the flux change. So it's trying to push it to the left, sort of to kick it back out of the field. So we know that the external force has to exactly balance this resisting magnetic force that's attempting to push the loop out of the field. And our expression for the magnetic force is BIL. And we know that the current induced in the loop is just the EMF divided by the resistance. And since this is motional EMF, the EMF induced is always VBL. And notice it's L and not 2L because we take the L in the direction of the velocity. So this would be, well, I have two B's and two L's multiplied together, so this would be B squared L squared over R times V. And V1 is that speed. And notice I took up some extra space here because we don't actually need it. When the loop is exiting the magnetic field, it's the same. Same argument. So the force would also be equal to B squared L squared over R times V1. Because as it's exiting, there will be the same magnitude magnetic force attempting to push it back into the field. And then when the loop is fully inside the magnetic field, so let's visualize this. This is a result we've definitely looked at before. But if it's fully in the magnetic field, well, there can't be any net magnetic force because the field is uniform. So any force on one side of the loop would be countered by any force on the other side of the loop. And also, there's no current. So there really couldn't be a force anyway. So either by symmetry or the fact that there's just no currents, we know that there's no external force applied. If there was, we'd be changing our speed V1. So we don't need it when it's fully in. And just for consistency, I'll make sure to call that external. All right. And now we'll consider what happens if the loop begins to exit the field, but we just stop pulling. So why will there be a magnetic force acting on the loop as it's leaving? Well, again, just think about this picture. We have the loop, and it's partially in and partially out. If we do an IL cross B force on this, we will see that there is going to be a magnetic force attempting to pull it back in. Because by Lenz's law, the loop will always resist a change in its magnetic flux. And also, if you just do this with the right-hand rule, we said that in this situation, there will be a a clockwise current induced. So if you point your thumb up in the direction of the current flow along the side of the loop indicated and point your fingers into the screen, your palm will push left, as we thought. So this magnetic force definitely exists. And I see that I drew my picture a bit too big here, so we'll just erase that here. So since there's a change in flux, the magnetic field will exert a force in order to oppose the flux change, so we get a leftward force. And now we'll come up with a differential equation that will give us the velocity of the loop. So in this case, we know that the net force acting on the loop will be equal to the mass of the loop times its acceleration. This is Newton's second law. Whenever we want differential equations involving speed, it is always Newton's second law. In terms of the net force, it's going to be the BIL force in the negative direction, because again, it is opposing the velocity, so we're just going to say it's negative because it's a resistive force. And then we found earlier that this force was equal to negative B squared L squared over R times V. And this time it's not V1, it's just the general V that can change. And then just by simplifying, maybe I'll simplify up here first. A differential equation means that you have to have a derivative in it. So acceleration is the rate of change of velocity. And then just to simplify, although this could be a final answer, I'll divide through by m, so I can get dv dt is equal to negative b squared L squared over mr times v. And this is actually not a terrible differential equation to solve. You could actually do the solution by inspection, but we'll go through the actual specifics here. So derive an expression for the loop's velocity as a function of time, meaning solve this differential equation. So our typical strategy for any differential equation is, well, hope it's separable and then separate, integrate, and solve. So it is separable because I can get all my v's on one side, and then I can put all of my non-existent t's on the other side. And then now that I have my variables separated, I can just integrate. So my v starts at v1 and it ends at some v of t that we want to solve for. And then my t's range from 0 to t. And notice I just factored all these constants out of the integral. So just doing our antiderivative, this would be ln of v. We'll drop the absolute value later because it is not relevant. And then if I integrate nothing, if I integrate 1 from 0 to t, well, that's just going to give me t. And then by applying the log rules, I would be subtracting two logarithms. So I'll just combine this as ln of the quantity v divided by v1 is equal to negative b squared L squared over mr times t. And then if we just take an exponential of both sides, we can eliminate the log, and then multiplying through by v1 gets us our answer. V of t is equal to v1 e to the minus b squared L squared over mr times t. And that's our answer. Notice we actually could have just seen this just by inspection, that this would be the answer. Because if we go up here, we're saying the derivative of something is equal to this constant times itself. And we know that's an exponential, just a pure exponential. And since we know it started from this velocity v1, we could just instantly know that this is v1 e to the minus b squared L squared over mr times t. So there is our little quiz on everything Faraday. So this isn't everything that could be asked, but It's certainly a good review of the general skills and questions we could be asked.